Alright, so we're going to start on some proofs today with what's known for lengths for the Hungarian-Mastrezania conjecture. But first I want to revisit the examples we did last time. So I think I sort of mucked them up. So let me do them properly. Okay, so alright. So the first example we'll do is the following. So take Q1 through Pn to be distinct integer primes. Okay. Now we'll consider the variety V to be the one-dimensional line, which is t plus 1, and the other coordinates are constant. The value is always equal to these prime numbers. Okay, so this is a one-dimensional irreducible subvariety of the n plus 2 dimensional torus. Okay. So now note that this set of coordinates satisfies no non-trivial multiplicative relations. But you can't throw any t or t plus 1s in there because you get some non-trivial rational function, and then these are prime numbers, which are distinct, they're multiplicatively independent. And so V is not contained in the proper torus context. Okay, so particular V is not atypical for V, and so therefore it has finitely many atypical points, assuming the conjecture is true. So then, by the DMZ conjecture, finitely many atypical points. Okay? So like before, now what's an atypical point? Well, if V is a line, so an atypical point means that these coordinates satisfy two independent multiplicative relations. These guys are always independent, doesn't matter what the value of t is, they're unaffected. So what the statement is saying, i.e., there are only finitely many t in Q bar, although already it's interesting if you restrict to t being integers or rational numbers, such that t and t plus 1 are both in the multiplicative group generated by these prime numbers. Okay? In other words, there's finitely many t's, such that t is a product of 2, 3s, and 5, and t plus 1 is also a product of 2, 3s, and 5s. Okay? Okay, questions about this? So you see that this conjecture sort of already has concrete arithmetic conjectures, arithmetic implications, and these sort of degenerate cases, as we'll see today as well, sort of play an interesting, important part in the conjecture. Again, just sort of trivialities that are really things to worry about. Okay, let me also say a few words about the second example we had last time. I'll do this briefly. So suppose that V in a three-dimensional torus is a generic curve, so it's not containing the proper torsion coset. And suppose that suppose that the union of everything is 1 over integer n of V intersect in sort of scaling, multiplicative scaling by n. If infinite, then you have an infinite sequence of points, Pn, n times Pn, in V across V. So then again, the conjecture, assuming it's true, there exists some atypical curve W inside V cross V, containing these points. Technically containing only an infinite subsequence of them, but subsequence. Again, the last time I sort of waved my hands. And what happened next? Let me explain what happened next. So, because W is atypical, and W is dimension 1, inside V, which is dimension 2, it means W satisfies two multiplicative relations. Okay. So on W, for all sort of points P prime on W, so again, these are points in three dimensions. You have two relations, P to the A, P to the A prime is 1, is also P to the B, P to the B prime. These are sort of three tuples of exponents. Because W is atypical. So then if you look at the P sub n's, the P sub n satisfy Pn to the A plus Na prime is 1 is Pn to the B plus Nb prime. Right, just because these points lie inside W. Just plugging it in. Again, now you can show that for big enough n, A plus Na prime and B plus Nb prime are not proportional. Sort of exercise in linear algebra. So the P sub n satisfy two distinct, sort of a two-dimensional set of multiplicative relations, and so P sub n is atypical for V. That's a contradiction because, again, by the BMC conjecture, V is supposed to have only finitely many atypical points. Okay? Yes?
Sorry, I think something wrong with my brain.
Yes.
What is P? Here's a point? Or?
Sorry, so P and P prime are points inside V. So there are three tuples.
Yeah.
And A prime, B prime are elements of Z cubed. So they're exponents. So this is like P1 to the A1, P2 to the A2, P3 to the A3.
Yeah. P prime?
Yes, that should be. Thanks. This is a P prime, and this is a P prime. Yeah? Did I miss any others? Okay. Yes, thanks. Other questions or corrections? All right. Okay, so I want to get to some proofs. So So yeah, again, this BMZ conjecture is sort of quite open at the moment. So there's been some progress towards it. And one case that's been settled completely is the case of curves. So we're not going to go through complete proof. I want to give sort of some ideas and partial results of how one makes some progress in this setting. So eventually, I'm going to use these guys' names. Eventually, we'll prove theorem 1. This is all due to Bombieri, Master, and Zagni. For the past like 20 years, I've been writing tons of papers. So the subject altogether independently. So suppose you have respect to V from C star to the N is a one-dimensional irreducible variety. And we're going to assume something a little bit stronger than it's not contained in any torsion coset. We're going to assume that it's not contained in a translate. So let me stick the word coset. In a coset of a proper algebraic subgroup. Okay, so not just by torsion points, but by any points. We're essentially doing this to avoid example 1 that we just talked about, to avoid dealing with that sort of arithmetic set. Somehow, if you use the stronger assumption, the question becomes more geometric. Okay? So I'll point out precisely where we need this assumption. So then, V has finitely many physical points. Okay, so this is sort of a goal for us. So it turns out that, at least for now, no matter how you approach this question, the theory of heights ends up playing an important role. I don't know how to make progress without it. And so this turns out to be related to something called the bounded height conjecture. And a result of it is as follows. One case of it is as follows. So suppose further, in this case, the Vn is a sort of one-dimensional, irreducible variety. And we're going to assume it's defined over Q bar. Okay? And not contained in a coset of a proper set. Okay, so then, we can define a subset, which we'll call Vn minus 1. So these are the points whose coordinates generate in at most n minus 1 rank subgroup multiplicatively. They satisfy at least one relation. In other words, is the union over T a proper torsion coset of V intersect T. Okay? So if you let this be the case, then for any point P in Vn minus 1, the height of P, and because V is over Q bar, the intersections are all defined over Q bar as well, so it makes sense of their height. The height of this point is uniformly bounded. Okay? What is it saying? It's saying take any one-dimensional curve over Q bar, not contain the coset, not transitive proper subgroup, and then look at all its intersections with n minus 1 dimensional torsion cosets. Okay, now note that this set really is infinite. Right? We're just like a one-dimensional curve with a codimension 1 variety, so there's really going to be tons of intersection points here. Okay? But it's saying, as you vary over these points, their height remains bounded. Okay, so let me point out a note or a mark. So this is false if V is contained in a proper coset. Okay, so this assumption really is necessary. As an example, you can take V, which is a set of x comma y, where x times y is equal to 2. So it's clearly contained in the coset of the group x times y is equal to 1. And if you look at the points 2 to the n, 2 to the minus n minus 1, and this is V. Well, these are all inside V, and they're also inside V, I guess, 1 in that case. These all, they all satisfy, like, this point is inside x to the power of n minus 1 times y to the power of n is equal to 1. And the heights of these are unbounded, right? And the height 2 to the n to the minus n minus 1 is equal to m log 2. We define it. That's going to infinity. Okay, so this really is false without the assumption, and that's somehow why. I think that's the only place where the argument I'm going to give don't get enough design is going to fail. Okay, so let's go to proving this theorem. Let me keep it up on the board. So there we go. Okay. So first, we're going to need some sort of basic lemmas for the theory of heights. Okay, so the first lemma is the following. So suppose you have a rational function, a quotient of two polynomials, q bar of x of degree d. So this is the, if these are co-prime, this is just the maximum of degree p. Degree q. Okay. So then x varies over q bar. The height of, r of x is at most d times the height of x plus a uniform constant that depends on r. So if you take a rational function and algebraic number, the height doesn't increase all very much. As a remark, this less than or equal to can actually be replaced by an equal to sign. I'm not going to need that, I think. Alright, so let's prove this. Now, q bar is algebraically closed, so we can factor stuff. So we can write r of x as a sum over m partial fractions, Cj over x minus j with exponents over each term, x minus aj with exponents j over here, plus some polynomial. Let me write the polynomial out explicitly actually. Plus the sum I goes from 0 to d of bi x to bi. Now because the degree of this is little d, we know that the sum of ej plus d is equal to little d. And just taking the rational function and decomposing it, partial fraction, polynomial. Okay. Okay, so now we're going to take the height and we're going to bound it by the right hand side. So the height var of x is most, what we showed before, so the log of the number of summons, which is d, plus sum of the height of each term individually, aj to ej. So just ruthlessly gonna apply the triangle inequality. Yes.
Why is this sum of ej plus d equal to little d? It's like if you have a repeated factor, won't like just the largest of the repeated factor actually be what they're summing?
Sure, the ages are distinct, right?
Do they have? Well, if they are, then shouldn't what's on top be a polynomial?
Oh yeah, I need like a double sum here, don't I?
Yeah.
Yeah. Sorry. So what I want here is like, yes, I want like a sum over R from 1 to pj of C like JR over X minus AJ to ER. That a little better? Sorry, yeah, sorry about that. Right, that's how the compilation works. Okay, so here I have a sum over J and over R of this kind of thing. Yeah, thanks. So I'll erase this sum over J and over R. Okay, so now we're gonna again apply. So we're gonna use the fact that height of x is height of 1 over x and apply the triangle inequality. So we get most something involving the heights of all of these guys, the bi's and the cjr, which is constant. So OB of 1 plus forgetting that really screwed me up. One second. Okay, well, let me finish with this proof. So I'm going to get something much weaker, but that's maybe fine. So sum over J and R of this height times R plus I times this height, taking out all the BI's and the CGR's, putting them into that big O of 1. And now the height of x minus aj, then most the height of x plus the height of aj plus 2. So in fact, we can erase this, incorporate that into the big O of 1. And so this is OV of 1. And I think the way I set it up so poorly, what I get is like a d squared height of x. If I keep track of how many x. Yeah. All right, so let me go back here just for the d squared right there. That'll be enough for us as well. All right. Sorry, yeah. So to recap, you sort of just write the partial fraction decomposition and just apply triangle inequality everywhere. Addition and multiplication. Questions? Okay. All right, so that's number 1. Okay, so now we need lemma 2, which says the following. So suppose V is a variety defined by f of x, y is equal to 0, where f of x, y is a polynomial into variables, with q bar coefficients, and the degree in the second coordinate of f is equal to d. So then, take points to the q bar points of v. Then the b height is big compared to the a height. We have, if you look at the a height and you divide it by d, you get something which is at most b height plus big O of 1. Okay, where big O depends on the variety V, but it's uniform over all points. Okay? Alright.
So it's not with respect to x less than d? D is like the total.
I think this is correctly written. Is it not?
Well, I guess we'll see. I'm just asking, is d the total degree or?
No, d is degree with respect to y.
Yeah, you just let d be that.
I'm sorry?
You just let d be that.
Yes.
Okay.
Just let d be that, that's right. Nothing fancy is happening. Alright. Okay. Okay, so I think I actually made the same mistake in this proof as the previous one. So let me give the proof next class. Sorry about that. All right, very much true, but we're going to assume it for now. Get back to it next class. All right. I proved theorem 2. This one I have correct. Proof of theorem 2. Okay, so the proof goes as follows. So suppose you have a point A1 through AN in Vn minus 1. So this is what's called a likely intersection. It's supposed to be a zero-dimensional thing, and it is. Okay, because in Vn minus 1, these guys satisfy some multiplicative relation. And so we can find integers mi not all 0 such that this thing is 1. Okay? So assume without generality that, say, Mn is the biggest of the Mi. Okay? Now the idea is that these exponents sort of can and do get as big as you can imagine, so go to infinity, but we're going to approximate this relation with one with founded exponents. Okay, so here's how it works. So you consider the set M1 over Mn, Mn minus 1 over Mn, and you can think of these as points in R mod Z, to the n minus 1. So now, by sort of pigeonhole, if I keep scaling these points, I can get as close to 0 as I'd like. So what I'm going to do is, so take B bigger than 0. B will be some very large guy we picked from the beginning, which we'll decide later what B is. B bigger than 0 to be a very large number. So then by pigeonhole, there exists Q, positive Q, most b to the n minus 1, such that for all I, if you look at Q mi over mn, this is within 1 over b of an integer. Okay? This is a standard pigeonhole argument. You divide R mod Z into b to the n minus 1 boxes of side length 1 over b. Two form the same box, you subtract, and you get this. Okay? So what does that mean? It means we can write QMI as some integer bi times mn plus some error delta I, where delta I is at most mn over b. Okay?
I'm sorry, can you
Yes.
just explain the pigeonhole thing again?
Yeah, so this is, I assume you have like, you assume n minus 1 is 2, so n is 3. You divide into a bunch of boxes of side length 1 over b. So there's b squared boxes here. And then if you look at all b squared translets, two must lie in the same box by pigeonhole. Then you subtract those, and you get one lying in this box.
And then you can surface 1.
Maybe b squared plus 1. Yes.
So you can include 0.
Sorry?
Include zeros on the positive cube.
No, I don't want you to do 0, right? That's trivial.
Okay, fine.
You're right, this one. Yeah. Yes, you get two different scaling lying in the same box, and you subtract those two, and you get one lying inside this box. This is called Dirichlet's box principle. We came up with to prove something or other. All right. Okay, so we have this relation here. So then what we're going to do is take our relation here and take it to the q's power and rewrite it. So we have 1 is the product over I of ai to the qmi. Now, these guys are all multiples of mn after some relatively small error. So we can rewrite this as the product of ai to the minus delta I is equal to the product of ai to the bi to the power of m. Okay? Now we take height. And what did we learn? Well, the height of this guy is the height of this guy. So we get that the height of this product is 1 over mn times the height of this product okay? So, which is less than or equal to, now applying the triangle inequality, 1 over mn times the sum of all these heights. Delta I, height of ai. Absolute value. And now we know that delta I is most mn over b. So this is at most 1 over b. So 1 over n. That is the sum of the height of all the coordinates. Okay? So in other words, we've created some, we can't quite control the BI, but whoever this is, we've created some product of the AIs whose height is quite small compared to the constituent height of the coordinates. Where these BIs are whatever. Less than or equal to b, because we assume that mn is the biggest integer. Sorry, BIs are at most, no. The BIs are at most, 2 is at most greater than 1 plus 1. BIs of this. Okay. Okay, so how do we use this? Well, So let C of X be the product of Xi to the Bi. Now, by assumption, C is not constant on V. This is where we're using that V is not contained in the proper torus subset. Okay? So the function of C from V to complex numbers is not constant. So now, the idea is to find an algebraic relation between C and each of the coordinate functions on our curve. Our curve is one-dimensional, so we get from 7 to degree 1, which means any two elements should have an algebraic relation between them. So concretely, what are we saying? We take J to be an index, not an N, and we look at the map from V to C squared, which take X to Xj of C. Okay? Now, because neither a coordinate element nor C are constant on V, but we get here with some irreducible curve, which is not contained, which is neither x equals something nor y equals something. Okay? So, in other words, so i.e., there exists some polynomial f in q bar of xy, so in two variables, with f of xj c is equal to 0. Okay? But now xj was a fixed function at the beginning in the variety V. So if you think of xj as a map from V to the complex numbers, it's got some degree. Every point has some pre-image. Right? So if you look at the map xj from V to C, has some degree. Let's call it V. And what that means is that for each value of xj, if you specify the value of xj, you have at most d points on V, which have that particular value. V defined to be that number. So in other words, for each value of xj, there's at most d points of C, which have that particular value. Okay? So for each value of xj, at most d values of C, which satisfy F. And what does that mean? What it exactly means, the degree of F in the second variable is at most D. Okay? This can be saved in sort of many algebra geometric ways. Sort of concretely, if you look at the curve inside here, which is the image, and you project it down to the xj coordinate, that's a d to 1 map. Which means, if you look at the polynomial defining, you'll get degree d. So this is sort of intuitively why it's true. In the Zania's book, he just says, by the Chow form. I don't know what that means. But he must. This is what he's saying. Questions about this? So I'm not going to give a formal proof, though. It's not too hard with complex analysis to give a formal proof. But yeah. Okay, so now by the previous lemma, which we haven't yet proven, we made a mistake. So by the previous lemma, what we have is that if you look at 1 over d times the height of xj, it gives a lower bound for the height of c up to an own 1 factor, which depends on c. Okay? of intuitively you should expect this, right? I mean, the more complicated C is, the bigger the height should be. Height of measure complexity. This is a formal way of making that exercise. All right, so now let's just rewrite this inequality right here. This is at most the height of the product of the AI to the BI. At the same time, we have this bound for every j. So now if we let d be the max over j of the degree of xj, viewed as a map from V to the complex numbers. Okay, this is at least 1 over nd and all of these heights plus O of 1. Putting averaging all of these guys for this case. Okay? Sorry, these are A's. Okay? Alright, so now number B was some fixed guy to be chosen later on. So now looking ahead at the proof, we're going to have picked B to be nd plus 1. And so as a result, subtracting this from this, what we get is the sum of these heights is bounded above by nd times nd plus 1 times O of 1 derivative b. Okay? Which is O of 1, so that's the end of the proof. So note also, not only is it the proof, but in fact the proof ends up being effective. Right? I mean, D can be computed right away, and so B can be chosen right away. And for each choice of C, we can make this argument right away, as long as the lemma is proved can be made effective, and I'll show you that again. So in fact, you can use the effective bound for that. Okay, questions? No the argument? The real somehow beef of the argument happens here. I'm assuming that you're satisfied a amount of the relation, but it's kind of hard to at first glance see what's going to happen. Alright, so next time I'll prove this thing that has been proved, and then we'll move on to the theorem 1.